Okay, ladies and gentlemen, this is problem 6, which is based on the textbook of Cengel and Ghajar, and it is supportive to the information that we've done with videos. I don't know what are the numbers, but the videos on internal forced convection of 2016. So with last year, take note, last year there were problems that I've put up, problems 1 to 5 of 2015. And please go through them because they are very supplementary to this work. And this is now an additional problem 6 that you can add to the series of problems. Okay, so in this problem, what we have is a tube, a circular tube, where we have water flowing at the inlet temperature of 20 degrees Celsius. It's water, and the volume flow rate is 12 liters per minute that flows through this tube, 12 liters per minute. Okay. The tube diameter is 25 millimeters, and the outlet temperature is 80 degrees Celsius. The tube length is 6 meters, but before I indicate the length, this tube is being heated with an electrical resistance element. Okay, or a current flows through it. And it is well insulated. So there's some very good insulation there. Okay. Making sure that there are no heat losses. Okay, so there's insulation. Okay. Oh, and the length of the tube, what I wanted to give, is 6 meters. So inlet temperature 20, it's being heated to 80, 12 liters per minute water, length is 6 meters, 25 millimeter diameter tube, and it's insulated. And what is asked from us is to determine the wall temperature on the outside of the tube, also here in the center, TW bulk, and you'll see why I've used that notation just now, and then also here at the inlet, the wall temperature at the inlet, so those 3 temperatures, and we are also asked to determine the heat transfer rate. You all understand the problem. Water being heated in a tube from 20 to 80 degrees Celsius, 6 meters, 25 millimeters, 12 liters per minute, and we are being asked to determine this wall temperature here, in the center, and at the inlet. Okay. Now, as you know by now, one of the simplest places to start these types of problems is to get the properties of the fluid that we are working with. Okay. Now in this case it is very easy because we can get it at the bulk temperature. And the bulk temperature would be the inlet temperature and the outlet temperature, 20 plus 80 divided by 2, so that would be at a temperature of 50 degrees Celsius. Okay. So the bulk temperature is 50 degrees Celsius of the water. At 50 degrees Celsius, we can go and look at the water tables in the textbook of Cengel and Ghajar, and typically the values are available in table A9 for different temperatures, and at that temperature you can go and get the properties for the density of the water as 988.1 kilograms per cubic meters. The thermal conductivity K is equal to 0.644 watts per meter Kelvin. The Cp value is equal to 4181 joules per kilogram Kelvin. And the Prandtl number is equal to 3.55. And then lastly, the viscosity is equal to 0.504 multiplied by 10 to the minus 3 kilograms per meter second. So we get the properties at the bulk temperature, The bulk temperature is the average between the inlet and the outlet temperature, 20 plus 80 divided by 2 at a temperature of 50 degrees Celsius. In the table A9, we can get the density 988.1, the thermal conductivity 0.644, the CP value 4181, the Prandtl number 3.55, and the viscosity μ equal to 0.504 multiplied by 10 to the minus 3 kilograms per meter second. Okay? But before we do the calculation, let's just do a few elementary things which we sort of know we're going to need, and that is determining the mass flow rate and the cross-sectional area and the surface area for heat transfer. Okay. So the mass flow rate is equal to the density multiplied by the volume flow rate. Now, normally in fluid mechanics, we use Q for the volume flow rate, but we've got Q in this course for heat transfer. Okay, so I'm using that symbol for the volume flow rate, cubic meters per second. Okay, the density multiplied by the volume flow rate in cubic meters per second. So it is equal to 988.1 multiplied by the volume flow rate. It's 12 liters. Okay, 12 liters is 0.012 cubic meters, and it's per minute, so we have to divide it to get it per second. Okay, so the mass flow rate works out as 0.1976 kilograms per second. Tell me if I'm going too slow or too fast, okay? Are you with me? Okay. So the cross-sectional area, cross-sectional area would be, if that is the tube, okay, would be the area through which the flow flows, the water flows. It is that area there. Okay. And that is equal to pi divided by 4 multiplied by the diameter squared. Okay. It's equal to pi divided by 4, and the diameter is 1 inch, 25 millimeters. So that is equal to 0.004909 square meters. And then the heat transfer area, the area over which the heat transfer is going to occur. So the area over which the heat transfer is going to occur would be this outside area of the tube. So if we take the perimeter multiplied by the length, we've got the surface area. So that is pi multiplied by the diameter, which is the perimeter, multiplied by the length. And that is equal to pi multiplied by 25 millimeters. The length of the tube is 6, so the area for heat transfer is equal to 0.4712 square meters. Okay, are you all with me? Right. Now, with many of these problems, when something like the heat transfer rate is asked, the first thing that people do think about is heat transfer coefficient. I need the heat transfer coefficient before I can calculate the heat transfer rate. In many cases, you don't have to do it, and this is a good example of it. The answer is before your eyes. Okay. So in this case, the heat transfer rate is just equal to the mass flow rate of the water multiplied by the Cp multiplied by the outlet temperature minus the inlet temperature. Now, before we do this calculation, let's draw a big graph, a large one, and I want to ask you to also do that because I'm going to put many values in it, and if you do too small, it's going to be difficult to get in all the values. Okay. So this is the temperature as a function of the length, or x, okay, and this would be 6 meters. Okay, and there's 0 meters. Okay. It has been given that the inlet temperature is 20 degrees Celsius. There's the inlet temperature, 20 degrees Celsius. Okay. And the outlet temperature is 80. However, the process that has been followed for the heating is a constant heat flux, because we've got this electrical wire. So if you think of this electrical wire, if the water see the first wire going around once, then it would get a certain amount of heat and its temperature will increase. When it gets to the second wire, it's the same thing. So every time the incremental temperature increase would be the same. So therefore, we have a case where the temperature increases linearly like that to the outlet temperature, which is equal to 80 degrees Celsius. Okay. And here, in the center, at 3 meters, we have the bulk temperature. And the bulk temperature we have calculated to be 50 degrees Celsius. You agree? Okay. Now, in terms of the colors, let's make this water blue. And that is sort of going to be the cold side, because the wall, the surface wall, is going to be at a higher temperature. Otherwise, it can't increase the temperature of the water. Okay, so this is the water side. Okay. Let's get back to the equation. Okay. Here we see what happened with the water. Its temperature increased from 20 to 80. Okay. And we've got the mass flow rate and the Cp. So it's very easy to calculate the heat transfer rate. So the heat transfer rate is equal to the mass flow rate, which is equal to 0.1976 multiplied by the Cp, which is 4181. Multiplied by the temperature difference, which is 80 minus 20. And the result is a heat transfer rate of 49,575 watts. Okay, please, you can calculate it like that, but please give me an engineering answer. So that would be 49.6 kilowatts. 49.6 kilowatts. Okay. So that is the heat transfer rate required over 6 meters to increase the temperature from 20 to 80 degrees Celsius. Okay, now we need the surface temperatures. Okay. And to get the surface temperatures, we will need the heat transfer coefficient, because we can say that the heat transfer rate is equal to the heat transfer coefficient multiplied by the delta T. And we've got the water temperatures, so that is how we're going to get the surface temperature. But before we can get the heat transfer coefficients, or heat transfer coefficient, we need to calculate the Reynolds number, because we need to know, is the flow laminar or turbulent? And even although the flow might be turbulent, from all those equations, we need to make the right selection. So let's do that. Let's calculate the Reynolds number. So the Reynolds number is equal to rho Vd divided by the viscosity. Okay, now we would say, oh goodness, we haven't calculated the velocity yet. Can do it, and I'm going to do it just now. But remember, we have also derived the very simple equation, which is in your textbook. It is equal to 4 times the mass flow rate divided by the viscosity pi and the diameter. And in many cases, we rather have the mass flow rate than the velocity. We can go and calculate the velocity. Okay, so there is how we're going to calculate the Reynolds number. So it is 4 times the mass flow rate. The mass flow rate is 0.1976 divided by the viscosity, which is 0.504, multiplied by 10 to the minus 3, multiplied by pi, and the diameter, which is 0.025, and the result is a Reynolds number of 15,480. Okay. Now everything, all Reynolds numbers more than 10,000 is being considered as fully turbulent. So this is definitely fully turbulent flow. Okay. Okay, if you don't like to calculate it like that and you would rather prefer getting the velocity, then you can also do that. You can just say the volume flow rate, is that the symbol that I've used previously? Yes, is equal to the average velocity multiplied by the cross-sectional area. Okay, the volume flow rate is equal to 12 liters, which is 0.012 cubic meters per minute. So we have to divide it by 60 to get it per second. There's the volume flow rate per second, is equal to the velocity multiplied by the cross-sectional area, which we've already calculated. And that is 0.004909, from which you can calculate the velocity as 4074 meters per second. Okay. So the density, there it is. The velocity, here it is. The diameter, there it is. The viscosity, there it is. You can calculate the Reynolds number also like that. Whichever you prefer. Doesn't matter. Right, now, we've got the Reynolds number. Now let's look at all these equations. If I've asked you now in the test or exam this problem, which equation are you going to use? Which one will you use? Which one?
The shortest one.
The shortest one, why?
The deepest filter one.
Why?
Because I don't have a lot of time. I want to calculate it quickly.
Brilliant answer. It's exactly what I'm also going to do here. Normally I'm lazy. Normally I'm lazy, and that's maybe the other way of describing it, isn't it? But if accuracy is not really that important, I mean, nobody is going to claim some money from you if we do this calculation now a little bit different or something, or nobody's going to sue you or anything like that, isn't it? So there's no risk. There's no risk. So therefore, it's exactly what I did. I choose the Dieterson-Boulter equation because it's just easier. Okay, so I'm going to choose the Dieterson-Boulter. Now, something that I neglected to mention, when I would also do the selection there, I would look at every equation in which Reynolds number range and Prandtl number range is valid. So if I remember correctly, the Dieterson-Boulter is valid for 10,000 and higher, and the Prandtl number ranges from 0.7 and higher. And if you look at the Prandtl number, you'll see we're in range, Reynolds number is in range, so you can select that equation. Okay, so just always check that. So let's select the Dieterson-Boulter. The Dieterson-Boulter is equal to 0.023, I think this is 0.023, is that right? Yeah, okay. So let's just go back here. Okay. So remember, I've just written this down. I actually think this is 0.023. Okay, so let's just come back to the calculation. 0.023, Reynolds to the 0.8, Prandtl to the n. Can you check in your textbook, is it 0.023 or is it 0.23? Which one is it? Oh, 0.023, yeah, okay, right. Okay, so 0.023 multiplied by the Reynolds and the Prandtl. Suddenly it just looks strange to me when I had to write it. Okay, so it is equal to 0.023 multiplied by the Reynolds. The Reynolds is 15,480 to the 0.8. Okay, multiplied by the Prandtl, and the Prandtl is 3.55 to the 0.3. Is that right? Good. Okay, so if we come back to the equation, okay, in this case, we're talking of the fluid for which we want to get the heat transfer coefficient. In this case, the fluid is being heated. So we need to use N equal to 0.4 and not 0.3. Okay. So let's just correct that, 0.4. And then the result is a Nusselt number of 85.83. Nusselt number of 85.83. Now we can get the heat transfer coefficient because the Nusselt number is equal to the heat transfer coefficient multiplied by the diameter divided by the thermal conductivity. Okay. The heat transfer coefficient is equal to 85.83. So let's put that in there, 85.83. It's equal to the heat transfer coefficient multiplied by the tube diameter, which is 25 moles, divided by the thermal conductivity, which is equal to 0.644. From that, we can get that the heat transfer coefficient is 2,211 watts per square meter degree Celsius. Order of magnitude is about right, okay, for convection heat transfer. Natural convection, heat transfer coefficients in the order of 1 to 10, order of magnitude up to 10. Heat transfer coefficients of fluids, gases through tubes, order of magnitude hundreds to thousands. We get boiling, condensation, two-phase flow, heat transfer coefficients in the order of magnitude of tens of thousands. Okay, so that's about right. So now, let's get this outlet, the wall temperature there. How do we do it? Well, very easy. We're just going to say that at this point there, we have the heat flux, we have that temperature, and now we've got the heat transfer coefficient, so we can actually calculate that temperature there. Okay. So the heat transfer rate is equal to the heat transfer coefficient in general, multiplied by the surface area for heat transfer, divided by T wall outlet minus T outlet of the fluid. I'm going to put in the values just now. Okay, so that is temperature of the wall at the outlet, at that point there. Now some of you might look at this equation and say, no, wait a minute, wait a minute. In total, there's about 86 kilowatts going through this thing. What you're actually now saying is with this equation, all the heat is going through that point there, isn't it? Okay. But remember, if we just write this equation a little bit different, then you will see it is the heat flux is equal to the heat transfer rate divided by the surface area. Okay. Is equal to the heat transfer coefficient multiplied by the wall temperature and the fluid temperature. Okay? And this is a constant heat flux problem. Remember, constant heat flux. You can go and calculate the heat flux now, but just the transfer rate divided by the surface area, but it's not necessary. So it's absolutely correct there. So let's go and calculate that temperature of the wall. So, and I'm going to do it like this. I'm going to say the heat transfer rate is equal to the heat transfer coefficient multiplied by the surface area, wall temperature minus the fluid temperature. So coming back to this equation here, I've just shown you the constant heat flux that we've got there. Okay. So the heat transfer rate we've calculated as 49,575. Okay. Is equal to the heat transfer coefficient, which is 2211, multiplied by the surface area, which is equal to 0.4712, multiplied by the wall temperature at the outlet minus the fluid temperature, which is at 80 degrees Celsius. Okay. And if you now go and calculate the wall temperature, then it would be 127.6 degrees Celsius. Okay, 127.6. Okay, so that temperature there is 127.6. Okay, right. Now, although we've done lots of calculations, I want to come back to the problem in terms of its fundamentals. If we look at a tube 6 meters in length, we have found that it's turbulent flow. So for turbulent flow, it takes only 10 diameters before the flow is fully developed. So in terms of the heat transfer coefficient, 250 millimeters, the flow will be developing. So the heat transfer coefficient in that region will be higher. Okay. The heat transfer coefficient that we've determined now are for fully developed turbulent flow. Okay. Now this 250 millimeters in comparison with 6,000 millimeters is 4% in the length. So the engineering assumption that we're going to make now is we are not going to be worried about this inlet. It's a negligible influence. Okay. And therefore that the heat transfer coefficient is a constant right through. And if the heat transfer coefficient is a constant right through, then the delta T should be a constant, like that. My graph, my line is not so nice, but it should be also a straight line. Okay. And this delta T here should be a constant. Delta T is constant. Okay. So the delta T stays constant. Okay. Now for that reason, I want to show it to you by calculating those two other values also. So now we use exactly the same methodology. We say that the heat transfer rate is equal to the heat transfer coefficient multiplied by the surface area. And now if we want the temperature there, we've got the fluid temperature there, which is bulk, which is 50. Okay. Is equal to the wall temperature at bulk minus the bulk temperature. Okay, and the only unknown, okay, so I'm running out of time. So the bulk temperature, that is what we want to calculate. And that temperature is equal to 60 degrees Celsius. What's it, 50? 50. Minus 50. Okay, and then we can calculate that temperature as equal to 97.58 degrees Celsius. Okay. And we can do exactly the same here with the inlet. The heat flux is driving this problem is equal to the heat transfer coefficient multiplied by the delta T. So the heat transfer rate is equal to the heat transfer coefficient multiplied, oh my goodness, multiplied by the area, sorry. Like that. Okay. And the wall temperature, that is what we want to determine. The fluid temperature at the inlet is 20. And then the temperature of the wall at the inlet would be 67.58 degrees Celsius. Okay. And for all of them, the delta T is a constant. And it is equal to 47.58 degrees Celsius. So this delta T here is 47.58 degrees Celsius. Okay. There's the wall temperature bulk, and there's the wall temperature at the inlet. Okay. There's one more thing that we need to do. We all follow. It's very simple. Getting now the wall temperature. If obviously you make the assumption the heat transfer coefficient is constant, in this case it's a very good assumption to make. Okay. Now, coming back to my choice of being lazy and using the Dieters-Boulter equation. Let's suppose you were designing something and you're trying to compete against another manufacturer. Then you need some accurate results, because that is how you're going to save material and make your product cost less. Okay. So let's suppose now we go and use Glinsky. So we redo with Glinsky. Okay, now I'm not going to write out everything for you. I'm just going to give you some of the most important answers, and you can go and do the problem yourself. Now, if you go and look at the Glinsky equation, you'll see there's a friction factor in it. So we firstly need to determine the friction factor. So the friction factor can be determined by that Petikov equation, which is equal to 0.790, the ln of the Reynolds minus 1.64 to the minus 2. And if we calculate it, it is equal to 0.02 0.795. There's a friction factor. Okay, Marilise, can you just go to the Glinsky equation for me, because it's going to take too much time to write it down. So let's look at the Glinsky equation. What do we need? We need the friction factor. We've just calculated it. The Reynolds number we have, the Prandtl number we have, friction factor we have, Prandtl number we have. We just have to plug it in. Okay, and I'm sure you can do that at home. Okay, so please go and do that. And if I didn't make a mistake, then you'll find that the Nusselt number, according to Glinsky, is equal to 89.97. Okay. So in this case, very close to the Dietersen-Boulter equation. I mean, it's just a 6% error. Okay. But they can be up to 25%. Okay. Okay. Right, from this, you can get the heat transfer coefficient as equal to 2318 watts per square meter degree Celsius. And if you now use that to go and calculate the wall temperatures, at the outlet it would be 125.4 degrees Celsius. At bulk, which is at the center, it would be 95.39 degrees Celsius. And at the inlet, the wall temperature would be 65.39 degrees Celsius. Okay, so there are the answers according to Glinsky. Now compare these values to the Dietersen-Boulter ones. Okay. You'll see about a temperature difference of up to about 3 degrees Celsius, 2 to 3 degrees Celsius. Okay? Any questions? Thank you, ladies and gentlemen.